Welcome back, Unit 11. This is your second of 5 topics or booklets in the Double Science Year 11 Physics course. This is what the front of your booklet should look like. So please fill in name, form, set and teacher on the front. You know it's the right one. It's got this year's on the front of the booklet at the bottom, so you know you haven't got any previous years. And just as a little window really into what we're going to be learning about, we're going to be learning about Sir Isaac Newton's 3 laws of motion and how forces affect objects in terms of their motion. So straight away you should be thinking about the previous topic where we learned about speed, acceleration, and the differences between the two. Well, we're going to learn how forces affect changes in speed and acceleration. Just moving over here to the right hand side, and this is the spec or specification which specifies what it is you need to learn. And rather than starting from the top, this topic is called Newton's laws. We're going to, firstly in lesson 1, pages 1 to 12 today, we are going to, even before we look at distinction between weight and mass, weight is one type of force, we'll look at what your previous learning in forces has been. And you have learned previously in school about forces and different types of forces. We're going to learn what are the units, what's the correct units for force, the Newton. So when we've done a quick recap on forces, we're going to be looking between what is the difference between weight and mass, the distinction between weight and mass of an object. Often in everyday language, the two are confused and misused. And to help us understand the difference, understanding that on Earth, 1 kilogram equals 10 newtons. That's on the surface of the Earth. And that's because the Earth has a specific gravitational field strength of 10 newtons per kilogram. We'll learn more about that later. And we're going to be using this equation here. Weight equals mass times gravitational field strength. The extra comment is that weight is the force of gravity acting on an object, whereas mass is the amount of matter in an object. So, as I've said, just fill in the front of the booklet. This is page 1 inside your booklet is exactly the same as page 1 in your previous booklet. It just shows you which equations you'll be given in the exam. And for foundation tier, we've already covered these first 3 equations, and during this topic you're going to be certainly using that one. You'll be using this one today. Weight is mass times gravitational field strength. And I think, I will have to check, that we'll be covering those two as well. I'd have to check on those two, so I'll just leave that off for now. but we'll certainly be using this equation today. This equation, F equals ma, is as a result of Isaac Newton's laws of motion, basically saying that the larger the force, the larger the acceleration. Okay, let's get on with business. Page 2 is just teacher feedback page, close the gap marking. So if you can write down here, lesson 1 on the left hand side, and date on the right hand side, and as always, underline. Keep your work well presented, please. I'm not going to read through the chapter summary. That's really there as a checklist for you. We're going to be doing that today and that today. So you can pause the video, read through that. It's in your booklet anyway. So, quick recap on what you've learned previously and looking at different types of forces. So, in general, a force is an interaction that causes a change and an interaction between objects. In mechanics, a force causes a change in the velocity of an object. Remember, velocity is speed in a particular direction. A force can cause the object to accelerate, decelerate, or change direction. These are the different types of forces. I'm not going to go over them. All forces are measured with a unit, the Newton. And in today's lesson, we're going to be learning about weight. Force is an interaction that causes a change. So if we look at these 3 photographs, it says the diagrams above show 3 basic forms in which a force could be exerted. These are if we look at this one, she is pulling, wrong pen, try again. She is pulling the chain. That person is pushing the button. And this person is turning. It's a turning force, sometimes called a rotational force. So these are a pull, a push, or a turning force. Now your first activity is this table here underneath. I just copied that over to the right hand side, just here, and you can see I've started to fill in parts of the table. What you need to do is complete the individual cells. I've done one myself here, and just give examples of push, pull, 2 pushes, 2 pulls, and 2 turning forces. That's to activate your prior knowledge of what you've learned previously. That takes you down to the bottom of page 4. Units. But what are the units for measuring force? Highlight the correct answer, then circle each of the other units and state what they represent. This is for you to do. I'd like you to pause the video now, because I'm going to complete this and I want you then to self-assess your responses against the correct answers. So pause the video now, please. Okay, you compare yours to what you see on the screen at the moment. You can see newtons has been highlighted because that's the correct unit for force. You can also notice there with newtons there's a capital N because it's the surname of Isaac Newton, a proper noun. The same actually for joules, you can see for energy. Just one point on this, you'll see there's a slight difference between speed, and I won't highlight it, otherwise you confuse it with the correct answer, with speed and velocity. Look at the difference. Speed is meters per second, that can be in any direction, but velocity is meters per second north in this instance. So there's a speed and a direction. So that's just going back to the last topic and reinforcing that understanding. So just moving down the page now, each force surrounding an object has a direction. You will see that forces act in pairs. You may remember from the previous topic, I've just talked about the difference between velocity and speed. Speed is a scalar quantity. It only has a size or magnitude. For example, 2 meters per second. So speed could be 2 meters per second. Velocity has magnitude, but a direction. So it could be 2 meters per second south, or east, or west, or right, or up, or down. It has to have a direction. Forces have a size and a direction. Therefore, forces are also a vector. Size and direction. Size and direction. Please remember that. In brackets it says, I'll highlight it now, the pair of forces have the same colour arrows that show the direction in which they act. This is an activity for you to do. What you need to do then is draw an object here and then colour in the two arrows, forces, which oppose each other. I've added in my drawing. This is my dog Joey, and he's got 4 forces acting on him at the moment. Now, because the forces, the arrows themselves, are the same size, the 2 purple arrows there are acting in opposite directions. So he's running to the right of the screen. So the force that he's exerting on the ground is pushing him to the right. That is this arrow number 1. But because he's moving at a constant velocity, the force acting to the left is cancelling out the force acting to the right, this one here. So that could be the air resistance acting against him. There's another 2 forces acting up and down, and you probably know what these are. We've got this force acting down here, that's the weight, and also you've got another force acting back up, because if there wasn't another force acting up, Joey would be accelerating downwards. We'll be learning more about that again, why he'd be accelerating downwards. Therefore, force 3 and force 4 are equal but act in the opposite direction. We're going to be learning more about this particular force today, weight. And then understanding why that weight and mass are are quite different in terms of their nature, their units, and in fact what they are. I must apologise there to Joey. He is a brown coloured dog, and I haven't done a very good job at putting him in his best light. Anyway, let's move on, and let's look at this exam tip. Look at the object before labelling up the forces surrounding it. Which direction is the object travelling in, and what substance is it travelling through? I'm going to change that there slightly. I'd put 2 arrows in previously. On your booklet, there are no arrows at all. The reason I've changed that arrow on the space shuttle is because that rocket or space shuttle must be accelerating upwards. And for it to accelerate upwards, the force acting upwards must be higher than the force acting down. So the arrow which I'm going to put on here needs to be smaller than the arrow acting upwards. And this upwards force is called thrust. That's the thrust coming from the engines and the thrusters here on the space shuttle. The force acting down, of course, is the weight. So the thrust must be larger, greater than the weight for the space shuttle to accelerate. Let's go back to the question. Which direction is the object travelling in, and through what substance? I'll just change colour a second to make this stand out. I'll choose a black pen there. So I need to say direction and substance. That's what you need to do, so that I'm not confusing the matter. I'll just take everything else off here. For the space shuttle, direction up, so substance is travelling through is air. Your task now then is to do the same for the parachutist and the skydiver and the swimmer. Direction and substance, please. Pause the video and complete. Check your answers against the ones I've just written in and self-assess. Now we can move on to a particular type of force, weight. Let's look at the units. Weight is a force measured in newtons, mass, kilograms, and gravity is measured in newtons per kilogram. And that will become clear. Turn over then to page 7 in your booklets. What you need to do is complete this table. I'll just do the first one for you. It's asking, this bag of potatoes weighs 5 kilograms. If you read the sentences above, it says decide whether they are scientifically true or false. Weight is measured in newtons, not in kilograms, so that's false. The actual answer should be given in newtons. That's the unit it should be given in. Can you now please do the same for 2, 3 and 4. What you should have found is question 2 is true because mass is measured in kilograms. You'll often find though, I think we're all guilty of it, we say my weight is say 90 kilograms or 14 stone or whatever, but weight really should be in newtons. So true, actual answer is correct. The car had a weight of 5,400 newtons. Yes, because weight is measured in newtons. True. Erica, the flea, weighed 0.06 grams is mass, not weight. False. Newtons. The next part is for you to do. You now need to write up a statement describing what mass is, and then a statement describing what weight is. A few little tips. Think about units. You could give an example. You can go back through this video, look through the booklet, or do a bit of research to help. Pause the video and complete. When completed, move down bottom of page 7. Now we're getting into the calculations. Use the weight equation, I'll highlight as I'm speaking. Use the weight equation to 1. Complete the triangle. 2. Complete the variable names with units. And 3. Isolate each variable. So that's rearranging the equation. So let's do that one at a time. Complete the triangle. Okay. Weight equals mass times gravitational field strength. So W equals M times G. M equals W over G. So I can write that down. W over G. G equals W over M. So we've completed the triangle. Check. Complete the variable names with units. We haven't done the units. Weight is measured in newtons. Mass is measured in kilograms. I see what we should have done here. It's okay. We'll write down weight next to that one, mass next to that one, and here let's, rather than write down gravity, let's write out gravitational field strength. So a little bit of a mouthful, but it is the correct name for that variable G. Let's complete these. There we go. And W over M. It wouldn't harm writing it down twice as we got there. Turn over to page 8 And at the top of page 8 is an activity for you to do. I've started it for you. Let's just read. We can calculate the force of gravity on Earth easily. There should be a capital E there. It's the name of a planet. Knowing that G equals W over M, or gravitational field strength, equals weight over mass, all we need is an object's weight in newtons, and mass in kilograms. So we need those two things. First example I've written underneath. That's for you to copy. For an egg, its mass in kilograms is 0.015. That's converted from grams by dividing by 1,000. We've measured its weight separately, and what we found out is, when we measured its weight using a Newton meter, its weight is 0.15 newtons. So we've divided its weight by the mass, and the gravitational field strength is 10 newtons per kilogram. Similarly, we've measured the mass and weight of a loaf of bread, divided the weight by the mass, and get 9.86. What I'd like you to do is complete cells that I'm highlighting at the moment here, and convert mass from grams to kilograms, or kilograms to grams, and calculate the gravitational field strength. What you need to do then, it says ignoring any odd results, so that's anomalous results, we shouldn't have any. We've calculated the Earth's gravity to be what you need to do there is add up the 1, 2, 3, 4, 5 different values of G and divide by 5 to find the mean value of gravity. You should find the true value is 9.8 to 1 decimal place. Oh, look, meters per second squared. Now, there is another permissible unit for gravitational field strength, and we will be using that value when we use F equals ma and so on later on in the topic. Anyway, I don't want to confuse the matter. That was just a habit. 9.8 newtons per kilogram. What does that mean? It means that every kilogram of mass has got a weight of 9.8 newtons acting down on it. Mass 1 kilogram has a weight of 9.8 newtons acting down on it due to the gravitational field strength of Earth. So you complete that. So 2 decimal places, gravitational field strength is 9.81 newtons per kilogram. Question 1, I've completed for you as an example, and you're going to be doing the others. So firstly, an astronaut has a mass of 67 kilograms sitting in her space rocket on planet Earth. That's a value for G to 1 decimal place. Calculate her weight, force. So just remember what we always do with calculations: equation, number, answer, there's your answer, and there's your units. That's how to get your full marks. Just a reminder underneath there of the equation you use. The larger a planet, the larger its gravitational field strength. Every object, anything that's got mass, has got a gravitational field that acts towards the center of the mass. Look at the size of Jupiter. Here's Earth. Let's say, so Jupiter is much larger in terms of mass than Earth. The larger the mass, the larger the gravitational field strength. And if you were to dig a hole right towards the center, theoretically, of a planet, you would, when you dropped an object down there, it would keep on falling until it got to the center. And if you were to dig a hole, a tunnel, no one's ever done it, right the way through, and you drop the ball down there, then it would stay in the middle, because everything is pulled towards the center of the planet. Person standing here, the reason they don't move towards the center is because you've got the floor, the surface of the planet in a way. So if I were to zoom in on that, well, that's supposed to be a person. You've got the weight acting down, and then you've got the reaction force of the surface of the planet acting back. They balance each other up, but more about balance and unbalanced forces again. Weight. What you've been asking to do here, calculate the astronaut's weight on Jupiter. Well, you've worked out the weight on Earth as 657. The astronaut's mass remains the same at 67 kilograms. The astronaut hasn't gone on a crash diet or gained a load of weight. The mass remains the same. What changes, of course, is the gravitational field strength. Here it is again, 24.8. So I'll let you complete question 2. Question 3, just be careful of question 3. Again, this is for you to do. I've started it, scaffolded it for you, just to help. Gravity in deep space is 0 newtons per kilogram. There's no gravitational field strength. This occurs because there's no massive objects nearby to attract other objects towards them. Calculate our astronaut's weight in deep space. And what is another term for this called? Well, I'll show you workings, but the weight should work out to be 0 newtons. And another term is weightlessness, or you might hear the term zero gravity, but weightlessness is what is used when you have an object or an astronaut in space with 0 gravity. Question 4, should be able to do that. Yeah, I'll leave that for you to do. And similarly for question 5. So we're now towards the bottom of page 10. Those pupils, not just set 1, but those higher tier pupils, need to do this next exercise, but even those pupils who are uncertain if they're going to do foundation, tier or higher tier, or even foundation pupils, please feel free to do this activity, and I'll just draw a little arrow down the side here to show where it starts and finishes. So starts there, top of the page. In fact, it starts even further up here, doesn't it? It starts here, partly down page 10. Those objects aren't going to mean much to you at the moment because it's not telling you what to do. So you've got six objects. You look at those 6 objects, and what you need to do is write the name of the object and details about the object into this table. I've done the Coke can, so the reason I know that row there is a Coke can is because the weight was down as 3.9 newtons. And I'm thinking, right, if it's 3.9 newtons, generally speaking, the mass is going to be weight divided by about 10. In fact, there's your Coke can, so 394 grams. And by dividing the weight of the Coke can by the mass of the Coke can, we've got 9.9. I've also done the same for this rather large cat, Meow the cat. 18 kilograms, because 18,000 grams. And again, divided weight by mass to get the value for geogravity based upon those 2 measurements. Again, calculate the mean value for G. So add 1, 2, 3, 4, 5, divide by 5, and then put the answer here. Use the range of values to state an uncertainty of your value of G. And there's a reminder here for you. Mr. Ruddy's kindly included this in the booklet. Uncertainty is half the range. Now the range is the difference between the highest and the lowest value. So here's the highest 10.1, there's the lowest 9.9. 10.1 take away 9.9 is 0.2, and half of 0.2 will give you 0.1. So you would write that down as whatever your mean value is here, you work that bit out, plus or minus 0.1 newtons per kilogram. So you write it out like that, but you would then calculate what goes there. Looks a little bit messy. Let me just smarten up the units. Newtons per kilogram. And then finally, plot a graph, I should say, of weight on the y-axis against mass on the x-axis, and draw a line of best fit. So we're looking now at question 3 and 4. And make sure a line goes through the origin. Well, I made a quick start. This is for you to complete, of course. And I've just plotted 2 points. There's the point for the Coke can. There's the one for the cat. And what I need to do is use a ruler and draw in a line of best fit. I'm not going to do that because we haven't got all the points. So remember, a line of best fit, you need to go through the origin. So depending on where the points are, you should have the same number of points above and below that line. Just a quick recap on line of best fit and the drawing of. And just to finish this lesson then. Question 5, calculate the gradient or slope of your best fit line. Compare your value with the mean value of G that you calculated earlier. The gradient of the line is the value of G. So you should find the value of G to be around about 9.81 newtons per kilogram, or it is saying there actually one decimal place, 9.8. Very quickly then, how you do that, you get, I'll actually draw it on here and then rub it out. So let's say the line of the best fit, I'll change the colour. Let's say the line of best fit was something like that. You would then take a point on the graph. You would look at the change in the y-axis, or the change in the weight. You would then do the same for the change in mass. So I could either draw that there, or I could draw it up here. Mass. Get a value for that. Get a value for that. You divide one by the other, and then you get your value for G by change in weight over change in mass. That's correct, isn't it? Let's just double check. W equals mg. I can remember that. Therefore, G equals W over M. Yeah. Okay, so that's the end of lesson 1. Please make sure, as always, you complete the plenary assessment. You should have done the starter retrieval before this video, and any supplementary videos that are included within the study zone. That's it for now. See you next time. Bye.